Okay, so recording chapters 19 and 20. Chapters 19 and 20. So chapter 19 is about free/forgetful adjunctions, which leverages something called the free functor and the free monoid thing. Do you remember those? I remember those.
I do. I certainly do.
That's actually a lie. I reread those, so I didn't remember those. But okay. Um, so I don't know. How do you want to approach this? Do you want to go through? I think at least this beginning it's important to go through.
Yeah, we should. We
So
definitely should.
we're gonna talk about something called forgetful functor, which is the left adjoint of the adjunctions, which again is the whole conversation about equality, equivalence, and all that stuff. A forgetful functor is usually a pretty simple functor that forgets some structure. This is still a little bit loose, and I don't know if I have an intuition about it. Um, Go on.
It's more about the number of laws that the source and target of the functor need to uphold. Like, if you have a bunch of laws that you have to uphold on one side, and you have to uphold fewer of them when you leave, then I guess that would be what you would call forgetful because you are forgetting some structure.
Oh, I was kind of with the mindset of collapsing that he mentions later in the intuition section, but you are right. That's a good intuition. So if
I
you have
mean,
more constraints and you're going to a looser place,
yeah, and if you are going to a loser place, there are fewer laws, which means there are fewer things that are different, right? Because if you have more laws, then you have more moving parts with which to make distinctions, right?
sure.
So the collapsing intuition does fit, but I think the whole number of laws is actually easier
Yeah, I
to
agree. I agree. That makes sense.
to hold in your mind.
Um, but categorical objects which abstract those sets have no internal structure. Oh, I jumped one sentence. So, for instance, lots of interesting categories are built on top of sets, and we've seen this before, right? And there was
Yeah.
even a name that I forgot. Set functor. Oh man.
Set valued functor.
Set valued functor. Yeah.
There is a
We've
functor that goes to the set category.
yeah we've seen this before. We 100% have seen this before. Cool. Those objects often carry the memory of sets in the sense that there is a mapping, a functor from a given category C to set. A set corresponding to some object in C is called its underlying set, right? So if you have a category C and you have an object that you can use a functor to go to the set category, that object that you are mapping will be called the underlying set of C. Monoids are such objects that have underlying sets, sets of elements. There is a forgetful functor U from a category of monoids mon to the category of sets, which maps monoids to their underlying sets. It also maps monoid morphisms, or homomorphisms, which I already forgot what they are. It's been a while. To functions between sets. Um, Go on.
Yeah, a homomorphism is a morphism that in some sense preserves the structure of its source when it goes to its destination.
No, that's the parallel of the injective function or something.
Yeah, yeah, yeah.
Yeah. I like to think of mon as having split personality. On the one hand, it's a bunch of sets with multiplication and unit elements. On the other hand, it's a category with featureless objects whose only object structure is encoded in morphisms that go between them. So this intuition right here, it's a bunch of sets with multiplication unit elements. This is the free monoidal thing, right?
Uh, yeah, kinda.
Because that's basically what a free monoid is. You keep using the generators to create sets that are sufficiently like you identify enough of them to have the associativity and the identity, but you keep
Yeah.
generating them. It's just a bunch of sets, right?
Yep.
And on the other hand, it's a category with features objects whose only structure is encoded in morphisms. Every set function that preserves multiplication in unit gives rise to a morphism in mom. So let's talk about that. Every set function that preserves multiplication in unit. Why that's the case though? It gives rise to a morphism in the monoidal category, in the monoid category.
Because if it didn't preserve multiplication and unit, then it's not really following the monoid laws, right?
But we only have two laws, right? Associativity and identity. Well, the identity element, right?
Yeah, but if you are not preserving the multiplication, which is the monoidal operation that is associative, and you are not preserving unit, then uh,
Yeah,
you are
makes
not really
sense.
following the monoid laws, which means even though that's a perfectly okay set function, it wouldn't really work if you go to
Mm-hmm.
the yeah.
Makes sense. Makes sense. So things to keep in mind. There may be many monoids that map to the same set. That makes sense. There are fewer monoid morphisms than there are functions between their underlying sets. I don't know if that makes sense, but that sounds okay thinking about it.
I mean, if you think about it, there are basically two kinds of morphisms between the underlying sets of a monoid, right?
Yes.
Those that preserve the monoidal structure and those that don't.
Yes.
Only the ones that do preserve that structure can be monoid morphisms.
Oh, okay. Okay, that makes sense. So because you have the ones that do not preserve the monoidal structure, you're going to have more functions between the underlying sets.
Yeah.
The functor f, that's the left adjoint to the forgetful functor u, is the free functor that builds free monoids from their generator sets. The adjunction follows from the free monoid universal construction we discussed before in previous chapters. So this is the image. This is the image.
This is the image.
And this is the expression, right? So this is the adjunction that we're trying to establish. In terms of home sets, we can write this adjunction as, right?
Yep.
So this is the home set of morphisms between the object fx and m, right?
Yes.
And this is the home set from the set category between the object x and um,
Yes. Where
right?
f and u are functors.
F and u are functors. So this is kind of what we are talking about. I think this image is way better than this one, by the way. Like I was reading it like this and I was kind of lost, and then when I like scrolled down and saw this, I said, ah, okay, I see. For every monoid homomorphism between the free monoid f of x generated by x and an arbitrary monoid m, there is a unique function that embeds the set of generators x in their underlying set of m. It's a function in set. So let's try to interpret that a little bit. So between f of x and generated by x and an arbitrary monoid m, so we're talking about these two guys right here, right?
Yes.
There is a unique function that embeds the set of generators x in the underlying set of m. It's a function in this guy right here.
Yes.
Uh, that makes sense because we're basically saying for a pair of f of x and m, there is a unique function in the blue guy here that exists between x and u of m for all the x's and all the f and a free in a functor f.
Yes. F is actually the free monoid functor. So
Okay, for every function that embeds x in the underlying set of some m, so we are now in the blue guy, there is a unique monoid morphism between the free monoid generated by f by x and the monoid m. So we're basically saying that there is a unique arrow in here between these two
yep.
here. Okay. The intuition is that f of x is the maximum monoid that can be built on the basis of x. If we could look inside monoids, we would see that any morphism that belongs to this guy embeds this free monoid in some other monoid M. That makes sense, right? This is like a top-down interpretation of this of the red guy.
Yeah, it is.
It does it by possibly identifying some elements. In particular, it embeds the generators of f of x in M. The adjunction shows that the embedding of x, which is given by a function from this set on the right, uniquely determines the embedding of monoids on the left and vice versa. Yeah, that's kind of like we've seen this before. We've seen this before.
Yes, we did.
So in Haskell, the list data structure is a free monoid. You've seen this before as well. A list
With
type.
some caveats. I actually read that blog post in between sessions, and yeah, bottom and laziness, they don't really play well with this whole category theory thing.
Interesting. I have to read those. A list type A is a free monoid with the type A representing the set of generators. Okay. For instance, the type char, list of char, contains the unit element, which is the empty list, and singletons like this one, generators of the free monoid. The rest is generated by applying the product, in quotes. Here, the product of two lists simply appends one to the other. Appending is associative, and there is a neutral
Unito.
element.
Yeah.
A free monoid generated by char is nothing but a set of all strings of characters from char. It's called string in Haskell, and that makes kind of sense. And then he goes to explain the same thing with the lists of units. And then he goes further to show that this guy is also isomorphic to additive monoid of natural numbers, which is true.
Yeah, funny thing. If you go to a dependently typed language, any dependently typed language, they actually define natural numbers as a linked list with no attached element. So, which is obviously isomorphic to a list of units, right?
Wait, you said that a dependency type language with
Yeah, because it's easier to prove things in terms of piano numbers, right?
no, but the
But
Bayano
if you think
numbers has new, right?
no, yeah, but a piano number is, if you think about it, is basically a linked list without the element.
No, but there is an element. As far as
No,
I
no,
can
no.
tell,
I mean,
the Pano numbers is used zero as the base
no, no,
case.
no. What I mean is like if you have a list, you have the empty list, right, which is new,
Yeah,
and then you have a cons of an element and another list, right?
yeah,
A piano number just gets rid of the element. You have zero, and you have a successor of another number.
yes, yes, yes. I see. And to finish this chapter, we're gonna talk a little bit about intuitions, which I think it's way cooler than well. This is okay. Like this is okay. This is kind of what we've seen before. But the intuitions are always better in my from my well from my engineering point of view. Which again is just hand waving arguments. Like this is there are no proofs. This is just intuitions, which is usually how engineers learn things.
I like
Uh,
intuition.
so to have an intuition about the forgetful adjunctions, it helps to keep in mind that functors and functions are lossy in nature, and we've seen this before with functions before.
Yeah.
Functors may collapse multiple objects and morphisms. Functions may bunch together multiple elements of a set. Also, their image may cover only part of their codomain. Uh, An average home setting set will contain a whole spectrum of functions, starting with the ones that are least lossy, so injections and possibly isomorphisms, and ending with constant functions that collapse the whole domain to a single element. We also know this. This is the cons
Yep.
function. I tend to think of morphisms in an arbitrary category as being lossy too. It's just a mental model, but it's a useful one, so that makes sense to me as well. We can only speak of morphisms that are invertible or non-invertible. It's that latter kind that may be thought of as lossy, right? Because if
Yeah.
if you are not losing anything, why can't you go back? That's kind of the intuition. Why the
Yeah.
non-invertible ones are by like intuitive makes sense to say that they are lossy.
Yes.
There is
Yes.
also a notion of mono and epimorphisms, which I don't know what they are. I don't know if we read this before in the book.
I think we may have, but I don't remember either.
The generalizes the idea of injective, so non-collapsing functions, and surjective, covering the whole codomain functions. But it's possible to have a morphism that is both mono and epi, in which is still non-invertible. Well, I don't remember what monomorphism and epimorphism means. I don't remember. Um, well, I'm guessing that monomorphism is generalizing the idea of injective functions, and epimorphism is the one generalizing covering the whole codomain. And it's basically saying that you
Probably.
can have both, and it's still not being invertible, which sucks.
Yeah, that does suck actually.
In the free adjunction forgetful adjunction, in the free, yeah, uh, this, whatever this is, adjunction, we have the more constrained category C on the left and the least constrained category D on the right. And that's because D is a set, right? Is the set category.
Well, yeah, in the usual example it is.
Morphisms in C are fewer because they have to preserve some additional structure, uh, which is what you said about the monoid laws, right?
Yeah,
In the case of Mon, they have to preserve multiplication in unit. Morphisms indeed don't have to preserve anything, so they are more like they are more free. They are more in number. It's a weird thing. It's like a feeling thing. I don't know how to explain it. Uh, when we apply a forgetful functor u to an object C in C, we think of it as revealing the internal structure of C. In fact, if D is set, we think of C as, as defining internal structure of C, its underlying set. In an arbitrary category, we can talk about the internals of an object, but other than though its connection to other objects, but this is just intuition. So this
this is
is a
just
very
hand waving. Yeah.
hand waving. If we map two objects, C prime and C, using U, we expect that, in general, the mapping of the home set, this, will cover only a subset of this, right? Because this has to cover more things, such as the monoidal laws.
Yeah.
That means that this will probably be a subset of this. That's because morphisms have to preserve additional structure, blah blah blah. But since an adjunction is defined as an isomorphism of particular home sets, we have to be very picky with our selection of C prime. In the adjunction, C prime is picked not from just anywhere in C, but from the presumably smaller image of the free functor f.
Which we
Uh,
just saw.
yeah, we saw that this is a top-down interpretation, right? So f
Yeah.
and then the thing down. The image of f must therefore consist of objects that have lots of morphisms going to an arbitrary C. Wait a moment. Not from just anywhere in C, but from presumably a smaller image of the free functor f. Yes, that makes sense because C prime is FD.
Yeah.
The image of f must therefore consist of objects that have very okay. In fact, there has to be as many structure-preserving morphisms from FD to C as there are non-structure-preserving morphisms from D to UC. Yeah, that makes sense. That is again that is the entire subset in the understanding thing. It means that the image f must consist of essentially structure-free objects. So there is no structure to preserve morphisms. Such structure-free objects are called free objects. And then finally, in the monoidal example, a free monoid has no structure other than the generated by unit and associativity loss. Other than that, all multiplications produce brand new elements. We've seen this before with three monoids.
Yeah.
And here's an example. So 2 times 3 is not 6. It's a new element. And this interpretation is very cool. This is very, very cool. Uh, um, well, it's basically saying that this is different than that. Which basically means a morphism from these three monoids to any other monoid M is allowed to map them separately, which is correct.
Yep.
But it's also okay for it to map both 2 and 3 to the same element of M, so like collapsing, or to identity 2 and 3 using addition. But then here's the kick. Free monoids, instead of performing the monoid operation, accumulate the arguments passed to it. So
Yep.
you keep gluing them together, but you don't know what to do with them. It may be concatenation, it may be addition, it may be multiplication. It doesn't really matter.
Could be and or, I guess,
Yeah, it
if
could
you're
be
dealing with
anything.
booleans.
And then the free monoid is basically holding them together as arguments that are ready to be applied to something in the future. So you're basically separating the notion of like accumulating the arguments and evaluation by itself. Almost like a lazy thing. Almost.
You could
Which
also
is
interpret it as building an expression tree, which is associative, so actually you can flatten it to a list, which is
that's
why
true.
the list is the closest thing to a representation of the free monoid
Makes
in.
total sense now, right? What
Yeah.
does accumulation uh,
Well, in a programming language, it looks like appending to a list, right?
yes, so that's very intuitive. And this intuition generalizes to other free constructions. We accumulate whole expression trees before evaluating them. The advantage of this approach is that we can transform such trees to make the evaluation faster and less memory consuming. This is, for instance, done in implementations of matrix calculus, where eager evaluation will lead to lots of allocations of temporary arrays to store intermediate results. Makes sense, right? You definitely, when you're doing matrix calculations, you rather simplify it, the shit first before doing the math. And if you did any engineering in university, you know this. It's a pain in the fucking ass. You rather take a shortcut and spend a little bit. Well, not. It's a shortcut in the long term, but it seems like a little bit more work in the beginning because you're not doing the calculation. You're just preparing it to be less of a pain in the butt.
Yeah, this is very obvious if you're dealing with matrix multiplication, right?
100%.
Not so much matrix addition, but multiplication definitely.
But what would be the simplification that you would do? I don't remember anymore. I remember that multiplication can be simplified like a ton, but I don't remember the
You
optimizations that you
want
can do.
to you want to exploit associativity to choose the order of the multiplications, and you want to do the ones involving the smaller arrays first.
Well, I guess. You want to do the you want to do the ones those ones first because
Because their results are smaller, right? Because the size of the result depends on the sizes of the inputs. In particular, the number of columns and the number of lines each depend on
oh, you're
one of
talking about
the.
doing multiplication of many matrices. I was just thinking just two. No, that makes total
No,
sense. That makes total sense. Total sense. I just didn't think of it. I was like, if you want to multiply five matrices, like uh, that does
yeah,
matter.
if you happen to accumulate the five in a list, you can just look, okay, which are the smaller ones? You can't reorder them, right? Because
The order
matrix,
matters.
the order matters, but they are associative, so you can choose
Yeah, makes total
how you're
sense.
going to nest them, and you just do it. So, okay, let's multiply the smaller ones first to cut down on the size.
Yeah, no, makes total sense. Makes perfect sense. I was trying to imagine like you can optimize, I believe, if you're only doing one multiplication pair with some simplifications and deltas and whatever that I already forgot most of it. But if you have many many matrices in a list, it makes perfect sense to do what you said.
Yeah, I remember. I remember this because I was reading Wikipedia randomly the other day, and I saw, oh, there's an article about matrix multiplication and about optimizing matrix multiplication. What's that about? And it turns out,
Yeah,
yeah, if you're multiplying lots of matrices, the order doesn't matter for the total result, but it definitely matters for how long it's gonna take to do the work.
yeah, 100%. Okay, and now chapter 20, which is very light in comparison to, I don't know, limits, colimits, adjunctions, natural transformations, a lot of stuff that we read before. Uh, this is way like lighter, at least for me, probably for Marinho as well, because we know what it's talking about. This is a very hot
Yeah,
topic. This is a very hot
yeah,
topic,
we
but I'm not gonna spend time because it's kind of nonsensical. The reason it's hot. And the book does a very okay job explaining this. It's just like people say that it's a mystical, like mystical beast that nobody understands. I do think you actually have an eureka moment when you understand it. But it's not like you're not rediscovering fire. That's not how that works.
Yeah, no, this is more like figuring out that, hey, actually I can put these things together uniformly. That's kind of surprising, right?
Yeah, it is surprising, which is cool. But it's not like, and there are many places. I'm not gonna point names and specific cases, but there are places in which people even acknowledge the fear that this term has, and just says we're not gonna have it, not because it's maybe hard to implement fast, or maybe because there's some complications in the compilation pipeline, but it's just because people are afraid of it. And to me, that's a bad reason, but
It's a burrito.
it's a very bad reason.
It's a burrito.
Yeah, no, this is a
It's
it
a
is
meme, right?
it's a meme.
It's a burrito.
And what is this about? All right, so what is this about? This is about composition. Like at the end of the day, as just the CT message is about composing things, monads are also about composing things. Surprisingly, well, not really, but and then we're gonna explore that a little bit. So then he talks about we like to make intermediate labels to save stuff, but then you can do point tree style definitions in functions in Haskell, which
By the
could
way,
not mean. Go on.
can I just say that flip is totally unnecessary? You could just
Unnecessary. I don't understand. I didn't understand. I think he got like, man, 4 is better than 3. I need another thing. And then he said, oh man, I know. Let me
you could
pick a
have
commutative
just
operation and just use flip on it.
no, it's not actually commutative, but the point is you could have just partially applied it on the left, right?
Oh yeah, this is
Using
exponential. This is not commutative. I bad. Exponentiation.
yeah, yeah, but the flip is totally unnecessary. You could have just done two carets in parentheses, and that would have done the job just as well.
Yeah. Yeah, I thought this was multiplication, but you're right. The order does matter, but
Well, not two carets, caret two, but anyways.
yeah, but you could have done this differently, 100%. And then we're gonna talk about it. And again, I also need to say this, and the book also says this itself. This is not to say that everything should be point freestyle.
I think it should, but that's just me.
Yeah, but you are a fourth person. You are like a concatenative programming language person. So to you, everything will be point free anyway. So, but this can get like. Have you ever played with like the double cons, the double composition? I don't remember the name. In Haskell, the symbol is usually this one, in which is basically the definition this, and then you say this equals that.
Oh, oh, it's the owl operator.
Yeah. The owl operator. That's a name for it, but maybe there is another name that I'm not remembering. When you get to that point, people start to get a little sus, a little sus, very suspicious. So then we're gonna go back to the Clinsley category thing with the writer that we saw before. Like we want to keep doing logs in the very seamless way instead of having to pattern match and reconstruct, pattern match and reconstruct. Um, and then this definition is pretty interesting. So the first thing that we need to be clear. Although we are writing things as these type of things, we actually treat a Classley arrow in the category K as a morphism between A and B, and M is just an extra. How can I say? It's the notation is telling you something, but we are not treating as there is something in there.
Yeah, you can't look inside of it actually.
Yeah. Well, in Haskell you kind of can, because I don't know if
But
he's
then
going to talk
you're
about it, but monads they do not. Two generic monads do not compose in a general case, which kind of
yeah, but
means
then
that
you
you
yeah,
have
but
to
then you
look
have to
inside.
yeah, but then you have to step outside of the context of having a single monadic functor, right?
Yes, that's true. Crazy arrows from a category only if we can define proper composition for them. If there is a composition which is associative and has an identity arrow for every object, we call the functor M a monad. So M is an endo functor, by the way.
Yeah, because it goes from the category to itself, and
Yes.
it's not. I mean, identity is still an endo functor because,
Yeah,
well, it goes from the category to itself, but
yeah.
it could be something other than identity. In this case, it is actually.
In Haskell, classical composition is defined using the fish operator, and the identity area is a polymorphic function called return, which again, in the very very long future, it may be removed. I know that in the near future, if you try to make return different than peer, a warning will pop up by default.
Yeah, because it turns out that every monad is an applicative functor, and
Yeah.
every applicative functor is a functor. So yeah, you need to be functorial, but anyways.
Yeah, no, but you can define a return different than peer.
Yeah, because type classes, right? They don't actually enforce the laws. They are followed by convention.
Yeah. So keep in mind there are many equivalents. Well, we're going to see this shortly, so I'm not going to read this. But it's important to notice the intuition about this. So this is the operator that allows us to seamlessly do the writer without having much trouble like pattern matching and reconstructing. And this is something to bootstrap a writer given a value. And then we have the laws, right? So associativity, left unit, and right unit
I
of
really
the
like how
fish.
the monad laws look when you use the fish, because they are literally just the category laws, right?
Literally the category laws.
Yeah, the laws of function
Oh, this is
composition.
identity,
Yeah,
and this is
return is
associativity.
just
Yeah,
yeah.
yeah. Wait, but associativity is not category; it's composition, no?
Well, a category is defined by its composition laws.
No, yes, but associativity, you don't. Wait, this is like chapter one or two stuff.
Yeah, in order to have a category, you need to have morphisms, you need to have an identity morphism, and you need to have morphism composition, which has to be associative and
Oh, so it
com-
does require to be associative. That's the missing part from my brain.
yeah, it has to be associative.
So this is yeah, I this is actually pretty nice then. This is actually pretty nice. Um,
Yeah, from a categorical point of view, this is definitely the way to define monads.
this is definitely the way. Yeah, but it's kind of inconvenient.
It is.
Which is okay. Like, it's not because it's inconvenient that it's worse.
Yeah,
It
but if
depends
you
on
step out,
the rule that you're using, right?
yeah,
Rule.
but if you step outside of category theory for a moment, we're gonna get to that in a bit. But I like the definition based on join actually. Um,
Yeah, we're
I
gonna
think
we're
it's
gonna go to that route as well, which kind of makes sense. Like we're gonna go there, it makes sense. But uh, I don't know. I am biased. I used too many binds in my life. So uh, anyway, so this is a monad is about composing embellished functions, which we've seen before, right? We're basically just
yeah.
naming things, but when we saw classic categories, we've seen this before. So this is the implementation of the monad, having the internal contents as a monoid using the fish operator definition. And then we also have a very cool function called tell, which basically allows us to add an argument to the log. Makes sense.
Yep.
Kind of makes sense. So fish anatomy, because now we're gonna dissect the operator. Yeah, that's what we're doing here. And then this is returns a function. So we're gonna have a lambda in here. That means, but now here's the kick. We need a
and
C. We need a C.
well, we need an A actually as the input.
No, we already have an A. It's here. We have an A.
Well, but you have. Oh, right, right, right. We need
Uh,
a C.
we need a
We do
C,
need a
but the
C.
C comes from here. But to get a C from here, you need a B. How can I get a B? Oh, it's using this. And this type of things is what people call type Tetris. Especially when you're talking about generic programming, in which like you don't have many options. You have a type signature, which is why I think that some authors of dynamic languages they 100% underestimate when they say that the types do not tell you something. They do tell you something. They will not solve your problem. If telling something means solving the problem, no, 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 that's not how that works. We need a human brain to solve the problem. or at least if the problem has some very specific patterns for us to make an automatic process to solve it. But reading the type, you actually get some information out of it.
Yeah, it does have useful information. It's just most type systems are not flexible enough for the people who like dynamic languages. I would be okay with using something like Idris, for instance, but then you have to go all the way to Idris, which is like not mainstream at all.
I mean, again, I'm not saying like Idris has a the dependent typed system, right? So that can tell you more information, but this already tells you shit ton of information, shit ton, which I think it's pretty nice because I can just and again, my mind size is that every single help that I can have, I want it. This is helping me, so I want it. That's kind of it. The discussion, if it's a worthy trade-off, it's a separate discussion. But I think it's kind of nonsensical to say that there is no information in here. Anyway, rant aside. At this point, we have to produce a result. Yeah, it's basically explain the type tetris that I just explained, right? And then we go to the realization that actually in Haskell we use bind instead of fish. And here's the implementation of bind.
I mean, fish is a perfectly fine function. I would use it.
I think I would use it as well. It's just because do notation exists, man. Uh, I think do notation kind of like asks for bind.
I'm of the opinion, this is not a fact, this is an opinion, but I'm of the opinion that names are the go-tos of data.
Names are the go-to of data. Okay, elaborate on that. We have time.
Well, in the same way that go-to leads to all kinds of messy control flow and loss of abstraction, right? Because if any function can go to anywhere at any point, then you need to know the internals of every function that you call. Otherwise, you may not actually do what you intend to do, right?
You said
Um,
that names are the go-to of data?
yeah, because names lets you do all kinds of complicated data flow in the same way that GoTo lets you do all kinds of complicated control flow. It's not as bad because you at least are
Ah,
not losing
I think this is a very unfair comparison. Like, but go on.
yeah, it's not as bad as actual go-tos because obviously you are not messing with control flow, but you can make data flow very complicated accidentally if you rely on names all the time.
Yeah, but it is kind of the opposite. The reason that go-to suck is because they add more stuff for you to remember. You are going through more paths of the code. You are going many more places. You are having to remember more things. That's why GoTo sucks. The reason that it's unfair, in my opinion, to compare that with names is because names are the complete opposite of that. I did all of this. I need a pit stop because my cache is I am out of cache. I did 50 computations. I want to get this piece of this block of code that's done. I'm going to give it a name, which is meaningful normally in English language, and then I can cache more stuff because I'm going to do 50 more computations.
But you have to. Okay, that's fair.
Go choose
Uh,
exemplify the lack of cache in human brain.
okay, on one hand, that's fair. On the other hand, you do have to come up with the name, right?
Well, I mean, you can do point freestyle all the way through it or fish and like, eh? If and then here's the problem, right? If you have 50 sequences of fish and the number 35 is broken, you have to rely very heavily on the error message saying a lot of details for you to know that it's number 35. And usually because we don't do that, what do we do? We go through the process adding a bunch of temporary names and printing them. Or we make them in variables and go to the debugger and try to look in the debugger the names as well.
Counterpoint, you really like threading macros.
No, but that's the thing. I never use threading macros going further than 5 operations because that's usually how long my cat. The only exception is if the operations that I'm doing are kind of simple, like I don't know, concat plus map, but then it depends. Is the mapping function that I'm using complicated? Because like it varies from threading macro to threading macro, but I would never do a sequence of 10 or like 15. Let's go 15. 15 immediate to advanced operations. I will never do that. For the same reason that I would not do 15 medium to complex operations in point freestyle.
To be fair, people writing forth consider that to be a fairly long function as well, like 15 calls in a row.
Yeah. So
They
I
would probably break that up into like 3 or 4 pieces, probably.
yeah. Well, I think everyone normally would do that. Like that I think that's a little bit of a. I'm not gonna say common sense because people can go crazy, but anyway. So now let's go to the join definition of this. So this is actually the explanation using fmap. That's why we are talking about join, because we want to implement this thing using fmaps.
Yep.
We want to exploit the fact that the m is a functor. That's what we want to do. But then here's the kick. This function generates another m, so you're going to have m of m, and that sucks.
You need a
So
way to collapse them, and that's what join is for.
and join does exactly that. And this is the type class definition using exploiting the fact that we have
A functor. Yeah.
functor. And here's the implementation. Uh, oh, this is implementing fmap using bind, which is also okay. And
Yeah,
this is the
because
implementation of join for the writer. Go on.
yeah. Yeah, because if you have bind, you kind of already have fmap inside of bind, right? This is just pulling that out effectively.
Yeah. Then we go to the do notation, right? And then it starts by saying that point free style can go very nuts as the owner owl operator. Imagine using 3 owls, man. That's kind of nuts. In a single point free style. Uh,
Yeah, point free and currying. I would say pick one of them. Don't try to do both because if you don't have multiple arguments to your functions and multiple return values, point free style gets really messy.
Wait, repeat the conditions if you don't have what?
If you can't take multiple values and return multiple values from each
Ah,
call,
okay, I see, I see, I see, I see, I see.
yeah, point free style gets really messy,
Yeah,
really messy.
that's very true. That's very true. I've been there. I've been there. Um, and then we go to the thing that I just said. Like people, there's a reason we give things names. It is like a hardware limitation, and do notation allows you to do that. So that's why actually maybe that's the reason bind is so freaking more common than fish, because bind allows you to be the syntax sugar for do notation. Although probably you can also use fish as the desugared version of do, but probably that would look weird or less performant.
Uh, Let me think for a second. It would probably.
Because you can define binding using fish.
You
So
can.
you definitely can make fish the base, like the bottom abstraction of do, but I don't know the intricacies of doing so. So anyway, um, so then we go to we're talking about the notation and all that stuff. The
I
ability
think
to give.
bind and not fish is because it lets you avoid intermediate values in some cases.
That makes sense. And then the question becomes uh, that do notation allows us to have very similar code to imperative code. And then the question becomes, why do you use monods at all? And the answer is because it allows us to have better control over side effects, which is an application of monads. Which is an
Yep.
application of monads. And why do we want control over side effects? That's a very good question. And today we have the time to talk about it. We want control over side effects because um, we want to know if the program is doing things outside of the program's realm. So this is a very insightful thing that I got years ago, which is the fact that you can interpret a program to some extent as doing the same type of calculations that you do in a piece of paper, right?
Right.
And what's the problem? The problem is that when you're doing math in a piece of paper and you are the one doing the things, and the actual outcome of that is useful because you can observe the paper as an outsider. Like, if you interpret the paper as an entity that for some random reason can think, the paper will not be able to remove its value to the outside world. There needs to be an extra entity, an outsider of the paper, that can do the observing. And why I'm talking all of these analogies? Because our programs do the same. Our programs need to connect to the database. It needs to do an HTTP request. It needs to read a file. It needs to ask the input from the user. So
Launch missiles.
launch missiles. So there is a need to the program to interact with the things outside of it. And why is that a problem? That is a problem because if it can control interact with things outside of it,
It can launch
many
the missiles
random
when you don't mean
things,
to. Yeah.
exactly, you can do any random things that you can think of, and then the program becomes unpredictable because maybe it's reacting to the effects that are happening outside. And that is the entire notion of a side effect. So that's why we want to have, like, it is a big deal to have control over the side effects. The, and again, the question kind of changes is it worthy to use monads to do so? That's a different question. That's a question that acknowledges that it is a big deal. And now we are talking about trade-offs. It's a different question, right? I don't know if the book will talk about this, but monads have problems. Monads have problems.
Yeah, they certainly do. In
Uh,
particular, you can compose monadic operations with themselves in the context of a single monad, but Lemos already mentioned this. It's actually tough. You can't really compose different monads together because the order suddenly matters, right? The order in which you nest the monad functors.
but I don't think it's necessarily because of the order. It's because how do you know? How can I explain this? In order to plug two monads that are the same, let's imagine I don't know an example here, maybe for instance, right? You know ahead of time how to create and destroy a maybe.
Yeah, you have the join, right?
You have in categorical terms you have the power of inspection. You know it is a maybe, and you are exploiting that fact. But assume that you have monads that are generic. You don't know how to inspect them. How do you connect the data, removing the embellishment, to go to the other one if you don't know how to remove the embellishment? And that's my
Yeah.
understanding on why the general case of monad composition, like different monads, it can be done. That's why you need to keep a stack of monads, which we call monad transformers, because you cannot plug them together in generally.
Which is why you have alternative like effect systems and linear
Exactly.
types.
Yeah, I don't know linear types yet though. I'm not there yet.
The idea with linear types is actually not that complicated. Basically, if you have a value of a linear type, you can only use it once. So what you do is you say, okay, I have a magic value that represents the
Mm.
entire universe, and it's linear. You can only use it once.
Oh, the linear is just because once you go forward, you can't go back.
No, it actually comes from linear logic.
No.
It's a kind of logic where you are not allowed to copy premises and you are not allowed to drop premises.
Okay. Well, that's good to know. Good to know. But anyway, then we go over using the fish operator and how that compares with do notation, because Well, for people that don't know Haskell, the things that are on the left of the arrow pointing to the left, it's without the embellishment. Without the embellishment. So there is that. There is that. And then we are basically just showing an example. And then it shows that the do notation desugares to the bind operator, and it explains what I just explained. There's also the this operator here, which is very useful, which is when you want to ignore the argument that is about to come from the bind, right? So you did some monetic computations, bind, you need a lambda, and you may want the result of the previous thing. So then you use you use the argument of the lambda, but maybe you don't.
Can I just say that it's really, really annoying that the double arrow operator is taken up by this monadic thing, and you have to use a triple arrow for the forward composition in Haskell.
Wait, forward composition? Are you talking about arrow stuff?
No, it's literally just dot with the arguments flipped. You write that as a triple arrow in Haskell.
Dot, but with the arguments flipped.
Yeah,
I don't know about that though. Are you sure? Is this in the prelude?
I'm not sure
I was
actually.
very certain that triple arrow is arrow type class.
No, actually, that's from category.
Oh, okay then. Well, that's fair to criticize, I would say. But this is very useful though. Like, this is very freaking useful. Uh, this is very useful.
I don't mean to say that that operator is not useful. I just mean it's unfortunate that that one has a shorter name when it's mostly used through the syntactic sugar. So you never actually write it down.
No, this
Yeah.
you do write this down a lot.
Oh, you actually do.
Yeah, I use this quite extensively. It is just that I don't know. Maybe in Spatula, in the programming language that we interpreted that we did, maybe there are some cases in there. But this is like it's very common to you to want to ignore this thing because maybe this is returning unit.
No, but the point is that if you're using do notation, you don't actually have to explicitly write that thing,
Yeah,
right?
but maybe you are not doing the notation. Maybe you are in the middle of a do notation, and you in one line you want to do fish or you want to do this. It
But you
happens.
don't need to do this in do notation.
No. You don't get it. You didn't get it. You are doing the notation as like your main control flow of the main body of the function,
Yeah.
but in one line you are doing a smaller operation that is also monadic. Then you use the fish. You use this.
But if you scroll up a little bit, you
Okay.
see it uses tel, right?
Mm-hmm.
In the middle of do notation with nothing after it. And
No, no,
that
no.
these sugars to.
No, in this case I agree. In this case I agree. I'm just telling you the use cases that the fish and this thing may be useful. You are either not doing the notation, that's the first, or you are doing the notation, but one of the inner expressions is actually doing two or three operations.
And I'm not saying that it's not useful, I'm just saying it's unfortunate that it
No,
has a
I
shorter name
know,
than
I
normal
know.
composition.
No, I know you're not saying it's not useful. I'm just trying to justify the reason that these two characters were picked. And then I don't know how common, which one is more common, the reverse composition or this. I don't know. I don't have this data.
Actually, you kind of do. Just look at F sharp.
I kind of do just look at F sharp. I don't know what you mean.
Forward composition in F sharp is just the double arrow, right? It's not the triple one, and people use it everywhere.
I don't know if I would say everywhere. I've seen pipes way more than the double arrows in F sharp. Uh, I wouldn't say everywhere, but again, I did that 2 years ago in a specific code base of the company that I was working with. So I don't know. Maybe I don't know what is actually commonly established. Maybe I don't know. We can ask Baguette in many videos though.
We can, yeah.
Okay, 6 minutes to go. And then we can use the notation with blocks, with braces and semicolons, which I particularly don't find very pretty and aesthetically
It is
pleasing.
it is useful for generated code though, because then you don't need to worry about significant white space, which is cursed.
Uh, that's a very hot topic. No, no, I'm not saying that for me it's hot, but the whole space-sensitive indentation is a hot topic. Uh,
It
even
is
if
annoying for, well, regardless of whether you like it or not. I'm not
it is annoying as
saying
fuck.
it is annoying, especially if you want to generate code, right?
Yeah, but like even people that hates Python usually I was in conversations that people are saying at least it has space sensitive indentation. I'm not saying I agree with them or disagree with them. I'm just saying that this is a hot topic, and I think I agree that well, first, if you are having at the point, if you are at the point that is annoying to ident space-sensitive languages, you're probably doing something wrong. You're probably not making separation of concerns in different functions or different files.
I'm not saying that it's annoying to write by hand. I'm saying it's annoying to generate by a program.
No, yes, but usually people are talking about the experience of writing the code themselves. But you are correct. It kind of gets like multiplied in annoyance because you need to generate that. It's probably a pain in the butt. Cool. You can use do block to simulate exceptions. Then we discovered that C++ features are from a monad, which is cool, I guess. And I didn't want to click on that.
But
Thank
you
you,
totally did.
thank you very much, sir. So let's go back. Uh, yeah, and then oh, and also very important to mention this. Do notation introduces a notion of ordering.
No, actually, composition introduces a notion of ordering.
Uh,
Because it is associative but not commutative.
you are right, but that's not enough because composition doesn't deal with the side effects, right? And we want the side effects to have a specific order of execution. We want that.
No, the composition certainly does deal with the side effects. It's just monadic composition is more convenient if you do notation.
Yeah, but monadic composition is what the monad is about. That's what we just read.
Yes, it is, but it's not because of do notation that you have ordering,
No,
it's
no, no,
because
no.
of composition.
Okay. If you're using the fish and not using the notation, you still have the ordering. That's fair. But what I meant was to say that monads and monadic composition, it introduces an ordering, keeping in mind the fact that side effects may happen.
Yeah, you basically turn the dependency on the order in which the effects must happen into a data dependency, right?
Yes,
Which is
yes,
what you want because Haskell is lazy. You need data dependencies to enforce that things happen in the correct order.
exactly. So you're correct. It's not the notation; it's the monad. But I would say that it is aesthetically more intuitive that this is happening when using the notation. That's what I meant to say.
Which is fair.
Um, and then it's basically saying that we have other applications such as nested loops, list comprehensions or generators. Uh, um, and then if you do not have the abstraction of the monad, you typically have to address these things with other parts of the language. And in Haskell, this is dealt by the libraries. And that's kind of it for today. So 1 hour, like we are 55 seconds from an hour.
We're
Next
actually
time,
on time for once.
yeah, for once we are on time. When the chapters are like really, really small and really, really like, we already know this stuff, so let's just go. So next time we're gonna talk about 21, maybe by itself. We're not gonna try to do 21, 22. I don't know.
Yeah, this chapter goes through a lot of stuff.
Yeah, but is it like how can I say can we talk about it in fast or can we need to talk a lot more about it and all that stuff?
Uh, I'll get back to you on that. Don't worry, but I'm not entirely sure actually.
Because if we can skip the, not skip it, but we can simplify it because we already know what the heck is happening. Maybe we can go 22. I don't know. Because 22 seems very heavy, right? It's basically the
All of
category
the
of
common
interpretation.
effects that people want to use, right?
No, this is 20. Yeah, this is 21. All the common effects. But I'm talking about 22 because that's the categorical monad, which I think it's probably it's harder to understand. We are 1 hour and 20 seconds in, so I'm gonna finish the recording now.
Bye, future people.